Hello friends, this is the first part of a lecture series on test questions pertaining to nuclear physics. For this particular part, I'll be focusing on nuclear stability and radioactivity. To begin with, we will first recall our uh, atomic model where we say that the atomic nucleus consists of positively charged protons and the neutral neutrons. As shown in this diagram, we assume that the nuclear shape is that of a sphere. So imagine the nucleus consisting of the positively charged protons and the neutral neutrons. The radius of the sphere is indicated by the letter R. So we call this the nuclear radius or the radius of the nucleus. Except for a hydrogen atom, which does not contain any neutron. Okay, a hydrogen atom has in the nucleus only a proton with its corresponding single electron that orbits the nucleus. We'll be needing also some quantitative properties of this subatomic particles, the electron, the proton, the neutron, and we include here the electric charge and the mass of a hydrogen atom. So we have here the atomic mass in kilogram as well as the atomic mass expressed in AMU or U. Our first question. It is well known that lead-206 with atomic number 82 and mass number 206 in oxygen with atomic number 8 and mass number 16 contain different atoms, and that the density of solid lead is much greater than the gaseous oxygen. So using the equation for nuclear radius, which is R approximately equal to quantity 1.2 times 10 to the negative 15 meters multiplied by capital A raised to the 1/3. Capital A represents what we call the number of protons and neutrons, sometimes called the mass number of an element, or also known as the nuclide number. So we have choices. Okay, letter A, the density of the nucleus in a lead atom is greater than that in an oxygen atom. Letter B, it is approximately equal to, or letter C, it is less than. So the main concept in answering this question is the fact that the radius, nuclear radius, is approximately proportional to the 1/3 power, the number of nucleons, labeled as capital A. Okay, nucleus contains. And also the volume or nuclear volume is approximately proportional to the number of nucleon, capital A. So using these two concepts, if we are to determine the value of the density for each nuclide, you will notice that the variable capital A will simply cancel out. And So our answer, the best answer therefore, is letter B, approximately equal to. Their nuclear density are just approximately the same. So we're going to show this in numerical computations in a little while. Alright, for our solution, we first find the nuclear mass for each atom. For the lead nuclide, the nuclear mass is just equal to 207 atomic mass unit, and that will be multiplied by 1.67 times 10 to the negative 27 kilogram per atomic mass unit, or AMU. And we will get as the nuclear mass of the lead nuclide, which is 3.46 times 10 to the negative 25 kilograms. Alright, for the oxygen nuclide, the atomic mass unit is 16.0 U multiplied by 1.67 raised to the negative 27 kilogram per U, and that gives us 2.67 times 10 to the negative 26 kilogram. We then find the nuclear radius for each of the nuclide. So for lead, the nuclear radius is equal to 1.2 times 10 to the negative 15 meter multiplied by the cube root of 207, and we will get as our answer the cube root of 207 is 5.92. Multiply that with this constant 1.2 raised to the negative 15 meter, we will get as the nuclear radius for lead, which is 7.1 raised to the negative 15 meters. Now for oxygen, following the same process, the atomic or the mass number or number of nuclei for oxygen is 16.0. Get the cube root of 16.0, that gives us 2.52, and multiplying it by the constant 1.2 raised to the negative 15 meter, we will get as the nuclear radius for oxygen, which is 3.0 raised to the negative 15 meters. We now proceed in finding the nuclear density, where the formula for density, of course, is rho is equal to mass divided by the volume, and that the volume of a sphere is 4/3 pi multiplied by the cube of the radius. And for lead, the radius, which was computed earlier, is 7.1 raised to the negative 15 meters. Get the cube of that, and then multiplied by 4/3 pi, right? The result will be the divisor, meaning 3.46 raised to the negative 25 divided by that. And we will get as the density for lead, nuclear density, is equal to 2.3 raised to the 17 kilogram per meter cube. Following the same process, we determine the nuclear density of oxygen, whose radius has been determined as 3.0 raised to the negative 15 meter. So we get the cube value of that, then multiply it by 2 or 4/3 pi, okay, and the result will be the divisor, meaning we will divide 2.67 raised to the negative 26 divided by that value of the divisor, and we will get as the nuclear density for oxygen, that is 2.4 raised to the 17 kilogram per meter cube. And as you can see, there is a very slight difference in the nuclear density for lead and for oxygen. So our conclusion, therefore, is that lead and oxygen have approximately equal nuclear density. Question number 2. For lead or Pb2O6 with an atomic number 82 and atomic mass equal to 205.974440 atomic mass unit, obtain letter A, the mass defect in atomic mass unit, letter B, the binding energy in MeV or million electron volts, and letter C, the binding energy per nucleon also in million electron volts. So the key concept we're going to use in solving this problem are primarily based on the definition of mass defect and binding energy. Okay, what do you mean by mass defect and binding energy? Well, we have here the simple definition for binding energy. It is just the minimum amount of energy that must be added in order to separate the nucleons, meaning the protons and the neutrons, okay, that are intact in the nucleus. So for a particular atom to have their protons and neutrons separated, okay, it needs to absorb, okay, an amount of energy exactly equal to the binding energy. Or, using our illustration, we have here a neutral atom where the protons and the neutrons are still intact in the nucleus. Okay? The energy that binds all these nucleons is the collective term for protons and neutrons. So the energy that holds or that keeps these nucleons intact is, of course, what we call the binding energy. Okay? And if you're going to compare the energy of the nucleus with all its nucleons still intact in the nucleus, compare that energy to the energy of the individual protons and neutrons already separated, you will find out that there is, okay, a difference in the mass. The total mass of the protons and neutrons already separated is always greater than the mass of the original nucleus with the protons and neutrons still intact. Why is there a mass difference? It is because whatever is that mass difference, sometimes called mass defect, that is accounted for by the what we call binding energy. That's why in our diagram, if you add the mass of the original nucleus with the protons and neutrons still intact, okay, that mass has an equivalent amount of energy, which when added to the binding energy would just be equal to the amount of total energy of the separated nucleons. So we are using here the conservation or the law of conservation not only of energy but also of mass. So law of conservation of mass and law of conservation of energy are both applied in this analysis. But we have a formula to determine what the binding energy, okay, of a particular nuclide such as lead. So we use this formula. Okay, binding energy is just equal to the mass defect. The one inside the quantity is what we call the mass defect or the mass difference. This simply represents the mass of total mass of the individual nucleons, meaning the mass of the neutrons and the mass of the protons already separated. All right, that is the meaning of Z capital M sub H plus capital N mass of the neutrons. When added, that corresponds to the total mass of the separated nucleons. And if you deduct the mass of the original nucleus with the protons and the neutrons still intact in the nucleus, then the difference is what we call the mass defect. And if that mass defect is multiplied by the constant c squared, okay, based on the famous equation by Einstein, E is equal to mc squared, or E is equal to delta m c squared. Okay, that is the basis for this uh, conversion of mass into energy. So the meaning of each symbol inside the parentheses is defined here. Okay, the value of c squared when expressed in million electron volts is just equal to 931.5 million electron volts. Right? So this is per mass or atomic mass unit, or AMU. So whenever you are to determine the amount of energy that is converted from a given amount of mass expressed in AMU, you can just multiply the given amount of mass defect or mass difference by this constant. So you will get the value of the energy already expressed in million electron volts, as we shall illustrate in the next slide, so as to show also the solution for each of the question A, B, and C. All right, so our detailed solution, we first label the atomic number of lead, which is 82, and the mass of hydrogen neutral hydrogen atom in terms of AMU is equal to 1.007825 AMU. Okay, and the number of neutrons, of course, is the mass number minus the atomic number, or 206 minus 82 gives us 124 as the number of neutrons. Okay, the mass of a neutron is given 1.008665 U, and the mass of neutral lead atom is equivalent to 205.974440 AMU. So, in determining the mass defect delta M, okay, you might be asking why we don't consider the mass of the proton, okay, that instead of the mass of the proton, why are we using the mass of a hydrogen atom, okay, a neutral hydrogen atom? It is because a hydrogen atom which contains one proton and without any neutron in the nucleus, all right, that is exactly uh, what we are using here, the mass of a hydrogen neutral atom, all right, which means that in using the value, which is 1.007825 atomic mass unit, this already includes, okay, this already includes the mass of one electron, the single electron that orbits the nucleus of a hydrogen uh, atom. Okay, this is in order to balance, right? To balance the presence of an electron, the mass of an electron, which is also considered in the atomic mass of the neutral lead atom. Okay, this mass of 205.974440 AMU already includes the mass of the electrons. How many electrons? 82. If there are 82 protons, there must be 82, what do you call, electrons, right? So that is the very reason why we consider, instead of the mass of proton, we are considering the mass of a hydrogen atom, so as to compensate of the presence of 82 electrons. Okay, the 82 electrons, the mass of those 82 electrons have to be eliminated. Okay, have to be eliminated when we compute for the mass defect delta M. The delta M should not include the mass of electrons. But since in neutral lead atom, there are 82 electrons, so we might as well consider the mass of the hydrogen. Okay, the mass of the hydrogen will balance, okay, the presence of those electrons. And so, since there are also 82 electrons, okay, to be multiplied to the mass of a single hydrogen atom, so the net effect is that mass of 82 electrons will not be included in our determination of the mass defect delta M. I hope that is clear why we are using the mass of a hydrogen, neutral hydrogen atom instead of proton. Okay, so when we substitute in this formula to determine delta M or the mass defect, so we just provide the necessary value of each quantity. All right. Z stands for the number of protons, or the number of what we call electrons as well. All right. So when we multiply this by that mass, 1.007825 times 82, we are already talking about the total mass of the protons and the electrons. Right? Now, for the number of neutrons, where there are 124, multiplied by the mass of each single neutron, okay, minus, okay, the mass of the neutral lead atom, which is 205.97, 44440 AMU, right? In this value of 205.974440, this already includes the mass of 82 electrons. So you will notice that we have here the mass of 82 electrons, but minus, okay, exactly the same mass of electrons. So in a way, the net result is we just eliminated the mass of 82 electrons. So what remains in our delta M will just be the correct mass difference or mass defect, okay, without any more the presence of the mass of the electrons. So we are sure that this only refers to the difference in the mass of the protons and the neutrons, meaning the mass of the nucleons, all right, when separated, minus, okay, the original mass of the protons and neutrons when they are still intact in the nucleus. So that value delta M is equal to 1.74167 AMU. This is the answer to letter A. How about the binding energy? So using the constant 931.5 million electron volts for every atomic mass unit, multiply that by the delta M, all right, we will get as the binding energy equal to 1,622.4 million electron volts. And finally, per nucleon, what is the binding energy? All right, since there are 206 nucleons, meaning the total number of protons and neutrons, so each nucleon will get this amount of binding energy, 1,622.4 divided by 206. That gives us 7.876 million electron volts per nucleon. So, what does this value indicate? This means that each, what you call, each nucleon, either proton or neutron, in the lead atom or lead nuclide, okay, there is an amount of 7.876, all right, million electron volts of energy, binding energy, meaning the energy that holds or that keeps each nucleon intact in the nucleus. If you're going to compare this value of binding energy per nucleon to all other nuclides, you will find out that this value for lead is among the highest. All right, among the highest uh, binding energy per nucleon. Okay, as we probably know, lead 206 is one of the most stable isotopes of what we call lead. Lead has several isotopes, and one of them is isotope 206. So isotope 206 is considered a very stable nucleus. The stability, nuclear stability of a given nucleus or nuclide is proportional to the amount of binding energy per nucleon, as you will find out in our succeeding discussion. All right, so speaking about the relationship between binding energy and the nuclear stability of a given nucleus or nuclide, we have this graph. Okay, the graph shows the relationship between the nucleon number, meaning the mass number of a given element, number of protons plus number of neutrons. Along the y-axis, you have the binding energy per nucleon in million electron volts. Okay, so as you can see, um, earlier we got the value for binding energy of lead 206. So lead 206 must be somewhere here, all right? Bismuth is 209, so a little closer to bismuth, okay? So all these nuclides whose binding energy are above 7, those nuclides with binding energies between 7 million electron volts and 9 million electron volts, they are considered very stable. That includes, if you notice in the graph, that includes the nucleus of helium. All right? There is a sudden, if you notice, there is a sudden peak in the binding energy of the elements when we start plotting the binding energy from the smallest nuclide, such as hydrogen. This is deuterium, tritium, lithium. Then there is a sudden spike for helium nucleus. All right, it's much higher than that of lithium, and it's already considered above 7 million electron volts. So, as we all know also, helium is a noble gas, and we know that helium gas is a very stable element. Not surprising because in terms of nuclear stability, we consider also helium to be very stable. So included here are the isotopes: oxygen, what's this? Phosphorus, potassium, iron, arsenic, strontium, tin, uh, what else? Uranium 238 also has relatively high binding energy per nucleon. We therefore say that as far as nuclear stability is concerned, we can say that the higher the binding energy per nucleon, the more stable a nucleus is. Why is this so? What makes a nucleus stable? It is because of what we call strong nuclear force. Okay? Among the four fundamental forces, strong nuclear force is the strongest. It is the force that binds the protons and the neutrons together in the nucleus. You might be asking, how come the protons, which are positively charged, why don't they separate? All right? In spite of the fact that there is an electrostatic force, a repulsive electrostatic force that's supposed to separate protons from each other. Okay? That only goes to show that there is a much stronger force that will keep protons intact, stronger than what we call electromagnetic force. And we call it strong nuclear force. So this kind of force, fundamental force, does not depend on the charge. Okay, so whether we're talking about the force between a neutron and another neutron, or probably between a neutron and a proton, okay, it doesn't matter which two nucleons we are talking about. Okay, unlike all other fundamental forces, however, strong nuclear force has a very short range, only in the magnitude of 10 raised to the negative 15 meters. But within this range, nuclear force, we say, is much stronger than the repulsive electric forces between the protons. Okay? But for longer distances, say for example, if two protons are no longer within that range of separation, then we say that the repulsive electric force, okay, will overcome this strong nuclear force. So it only becomes significant if the protons are relatively very, very close to each other. So we'll be explaining more about nuclear stability, including nuclear activity, in the next slide. To describe the stability of nuclides, we refer to this chart known as the Segre chart. An Italian physicist by that name, Segre, has invented this relationship of the number of protons, labeled capital Z, plotted here along the x-axis, and the number of neutrons along the y-axis. So there is a relationship between those two nucleons. The red line indicates that when a nucleus has the same number of neutrons and protons, right? As we increase the number of protons, there seems to be a degree of low, what we call stability that happens, right? The dotted points, colored blue, indicate number of neutrons relative to the number of protons where a given nucleus becomes more stable. Alright, so it looks like that as we increase the proton number or the atomic number of an element, okay, there will be the stability of that nucleus becomes less and less. But in order for that nucleus or nuclide to be stable, it needs more neutrons. So we say that as the mass number A increases, stable nuclides have an increasing ratio of neutrons to protons. Okay. As nuclei get larger, okay, that is indicated by the increase in the atomic number or proton number. As nuclei get larger, more neutrons will be needed for the nuclide or nuclei to be more stable. So it looks like that the neutrons act like glue. All right? The neutrons simply behave like glue that will keep these nucleons intact in the nucleus, meaning for a given nucleus to be more stable, as the number of protons increases, okay, the ratio of the number of neutrons to the number of protons must be higher for it to become more stable. Okay, so if you check in the periodic table of elements, you will see there that among nuclides or nuclei with very high atomic number, okay, those above 83 atomic number, those above 83 are already considered radioactive. It is because as the number of protons increases, there are protons that are already quite far from each other. So the presence of the strong nuclear force no longer is already overcome by the force of repulsion of two protons. So what happens is that those nuclei become very unstable. In other words, the nucleus will just split, all right, spontaneously, because the presence of the repulsive force among protons dominate the existence of strong nuclear force, especially for protons that are relatively far from each other. So the more protons there are in a given nucleus, okay, the more unstable they become. But the presence of neutrons make these elements also stable, neutrons are acting like a glue, the glue that holds these nucleons intact. But neutrons by themselves are also unstable. So you will find out that in our discussion of radioactivity, okay, there are nuclei that are unstable, naturally unstable, okay, meaning that they spontaneously undergo nuclear transformations. That will be our focus of discussion in our next questions coming in the next slides. Question number 3. The nuclide radium-226 when atomic number 88 decays by alpha decay. Question letter A. What is the atomic number and the mass number the product nucleus. Letter B, calculate the amount of energy corresponding to the mass defect. We are given the masses, atomic masses. For radium-226, the atomic mass is 226.025410 U. Now for radon, its atomic mass is 222.017578 U, and of course for helium nuclei, or a single helium nucleus has a mass of 4.002603 AMU. So our first task is to determine the atomic number and mass number of the product nucleus. Our key concept, of course, is the definition of an alpha decay. When we say a nucleus undergoes an alpha decay, it simply means that the original nucleus is unstable and that it's going to spontaneously emit an alpha particle, okay, to attain stability. This usually happens in nuclei which have large nucleon numbers. Okay, large nucleon numbers such as radium, whose nucleon number is 226. Alright? So during alpha decay, take note that the nucleon number of the product nucleus, sometimes called the daughter nucleus, will decrease by 4, and that the proton number decreases by 2. And this is represented in this equation. Letter P stands for the parent nucleus, whose number of protons labeled capital Z, and the mass number or number of nucleons labeled capital A. So when it emits an alpha particle, okay, the resulting daughter nucleus will have an atomic number that is Z minus 2, because it decreases by 2, and the mass number decreases by 4. If we are to apply the law of conservation of mass, okay, all we need to do is just add the superscript. For example, A minus 4 plus 4 will result to A. Alright, so that indicates that for the mass numbers, we say that the mass number here is conserved. And for the atomic number, Z minus 2 plus 2, of course, is equal to Z. So the number of protons also indicate that there is a conservation of charge indicated in this nuclear equation. So our solution for letter A is simply to determine the number of nucleons. When radium emits alpha, that means the resulting nucleus, which in fact is radon, Rn is radon. So since the mass number will be decreased by 4, from the original mass of 226, it should now become 222. Because if we add 222 plus 4, we'll get 226. Alright? But the number of protons from 88, it now becomes 86. Because we say that the atomic number or the proton number is decreased by 2. So from 88 becomes 86. But if we check 86, the mass atomic number of radon and the charge of helium, which is positive 2, we still get the original number of protons of radium, which is 88. Alright, so the resulting element, or the what do you call the daughter, is called the daughter nucleus, is no other than the element radon, which, by the way, is also very unstable or radioactive by itself. For letter B, we first determine the mass defect, delta M, and that is determined by just getting the difference of the mass of what we call the original nucleus, meaning the atomic mass of radium, that's given 226.025410 AMU. Right? So the combined mass of radon, which is also given 222.017578 U, and that of a single helium particle with a mass of 4.002603. So adding these two masses and then subtracting that from the original mass of radium, we will get a positive delta M. A positive delta M amounting to 0.00052229 AMU. Positive means that in this process, we say that alpha decay is energetically possible. So it is possible for radium-226 to emit an alpha particle because the resulting mass of the daughter nucleus, meaning the mass of radon, combine that with the mass of an alpha particle, it is way below the original mass of radium. Okay? We say that if the mass of the original nucleus is higher than the mass of the product nucleus, including the mass of the emitted alpha particle, is higher, where delta M is positive, we say that energetically this alpha decay is possible. So with this delta M, which is positive, we now convert this into its equivalent in million electron volts by just multiplying that by 931.5 MeV per AMU, and we will get 4.871 million electron volts. So this is the answer to question letter B, the amount of energy corresponding to the mass defect. The mass defect, which is 0.00052229, all right, has a corresponding energy released. This 4.871 million electron volts is the energy combined in the form of kinetic energy of radon and the alpha particle. In other words, radon, after the alpha decay process, we can imagine that radon, okay, the nucleus radon is moving at a certain amount of kinetic energy, right? Together with the kinetic energy of the moving alpha particle, okay, their combined energy, kinetic energy, amounts to 4.871 million electron volts. If there's a question about their specific kinetic energy, then we can just apply the law of conservation of energy and the law of conservation of momentum to determine the individual kinetic energy First, by determining the velocity of each product, radon nucleus and alpha particle. But that is not required in this particular question. So we just are interested in determining the energy released, okay, as a result of radium emitting an alpha particle. Okay. The resulting daughter nucleus, which is radon, also has its own share of the energy, 4.8721 million electron volts. Question number 4. The atomic mass of carbon-14 with atomic mass 6 and mass number 14 is 14.003242 U. Calculate the energy released in the beta decay of carbon-14 given that the atomic mass of nitrogen, whose atomic number is 7 and mass number 14, the atomic mass is 14.003074 U. So, just like in question number 3, the key concept this time is the definition of beta decay. What do you mean by a beta decay? So this type of nuclear transformation occurs in nuclei which have an excess of neutrons. A neutron in the nucleus changes into a proton. Take note again, the neutron in the nucleus changes into a proton by emitting a beta minus particle. When you say beta minus, that's also equivalent to an electron. Okay? A beta minus or electron particle being emitted. So we take note that the nucleon number of the product nucleus or the daughter nucleus will remain the same, right? But the proton number will be increased by 1. So the general formula is indicated here, where P is the parent nucleus whose atomic number is capital Z and the nucleon number is capital A. So upon emission of a beta minus or an electron, the daughter nucleus will have a nucleon number that remains, no change in the nucleon number. Alright? But the atomic number will be increased by 1. If Z was the original atomic number of the parent nucleus, the daughter nucleus will now have atomic number of Z plus 1 with a mass number of still equal to A. So for our example, we have carbon-14, okay, atomic number is 6. When it emits a beta minus particle or an electron particle, it becomes nitrogen 14 with an atomic number of 7. Take note, when we add the nucleon number 14 plus 0, it still is equal to 14, the original nucleon number of carbon. When we add the atomic number 7 plus negative 1, we have atomic number 6, which is the original atomic number of carbon. So, our task is to calculate the energy released in this nuclear transformation, beta decay. So, we get delta M, or the mass difference. The mass of carbon-14, original mass of carbon-14 is given as 14.003242 U minus the mass of nitrogen, the daughter nucleus, which is given as 14.003074. So the difference will be 1.68 times 10 to the negative 4 atomic mass unit, or U. There was no need to include the mass of an electron because after all it is very negligible, relatively speaking. Alright, so with this given delta M, we can now determine the energy that is released in the process of emitting a beta minus particle. We simply multiply 1.68 raised to the negative 4 AMU by 931.5 MeV per 1 AMU, and we will get the answer as 0.156 million electron volts. This is the answer to our question, the energy released during the beta decay of carbon-14 as it transforms into an entirely new nucleus, which is nitrogen-14. This energy, again, is in the form of kinetic energy, right? 0.156 million electron volts can be interpreted as the kinetic energy of nitrogen-14, all right? Of course, an electron that is produced also has its own kinetic energy. So strictly speaking, if we add the two kinetic energies, that of nitrogen nucleus and that of an electron, okay, the total will actually be equal to 0.156 million electron volts. This is our last question. Nucleus with atomic number capital Z and a neutron number capital N undergoes two decay processes. The result is a nucleus with atomic number Z-3 and neutron number N-1. Which decay processes may have taken place? Letter A, 2 beta minus decays. Letter B, 2 beta plus decays. Letter C, 2 alpha decays. Letter D, an alpha decay and a beta minus decay. And letter E, an alpha decay and a beta plus decay. So, if you're going to represent in the form of a nuclear equation, the parent nucleus, whose atomic number is represented by capital Z, and whose nucleon number is N plus Z, where N is the number of neutrons, Z number of protons. Alright? So, when it undergoes two decay processes, alright, the daughter nucleus will have an atomic number that is Z minus 3, right? In other words, its atomic number will be decreased by 3, and its nucleon number will be N minus 1 plus Z minus 3. Okay? A decrease of 1 in the number of neutrons and a decrease of 3 in the number of protons. Right? So, what or which decay processes may have taken place from among the choices that we have given, A, B, C, D, and E. Alright. So we say that in an alpha decay, okay, in every alpha decay, 2 protons and 2 neutrons are lost. Which means that the atomic number Z and the number of neutrons each will decrease by 2. While in a beta plus, sometimes called a positron decay, okay, in a beta plus decay, the number of proton changes. The proton changes to a neutron. That means the resulting atomic number of the daughter nucleus, the atomic number is decreased by 1. And the number of neutrons is increased by 1. So if we combine, okay, the number of protons that is decreased, notice that here in the first decay, that is in every alpha decay, the number of protons is decreased by 2. Plus in the beta plus decay, it decreases by 1. So we have a total of 3 protons decreased. Alright? And that agrees with our equation that the daughter nucleus will have a new atomic number Z minus 3 because the net effect is for the number of protons to decrease by 3, while the net result in the number of neutrons in the alpha decay, there is a decrease by 2. Alright? In the B plus decay or positron decay, there is an increase of 1. So the net is a decrease by 1. Alright? And if you're going to check in our formula here, the net effect on the neutron is decreased by 1. So n minus 1, while the number of protons is decreased by 3. Alright? So our notation for the daughter nucleus is satisfied. Okay? When we analyze the net number of protons and neutrons that have changed, and this happened, okay, these particular changes in the number of protons and neutrons correspond to 1 alpha decay and 1 beta plus decay. In other words, the best answer to this question is letter E. Alright, so that will be all for today's discussion of questions. Thank you very much for watching.